Hopefully you had a chance to, at the very least, to sort of maybe read them over and think about things, I guess, a little bit. It's really just a sort of chance to review some stuff from grade 11. Does the car speedometer measure speed, velocity, or both? Well, it's called a speedometer because it only measures speed, right? So if we're going to measure velocity, you'd have to include the compass that many vehicles now have, right? If an accurate speedometer registers a constant value for a period of time, can you determine the average velocity over that period of time using only the speedometer? No, you cannot, because speedometer only measures speed. Basically, 1 and 2 are the same question. Right? Can you determine the average velocity over that period of time? No. You need the direction. Can the average particle of a particle, an object, be 0 over a given time interval if it's not 0 over a shorter period of time? For example, let's say you go from 0 to 60 seconds, and the average velocity is 0. But between 10 and 20 seconds, the average velocity is, say, 5. Is that possible? Josh says yeah, Bailey says no. No, Bailey? Explain.
Because an average is taking all your factors together, adding them up and dividing them, so you're going to be getting a factor anyway.
Okay. Josh? What say you? The battle of the...
Go against the system.
Oh, you're just being saying no because turns out you're right.
What?
If I go forward, right, and my speed during my average velocity in the outlet interval there is +5, but then I turn around and I go backwards, same speed, my average speed is now -5. And Bailey, you were thinking about everything being positive values, I think, right? So if you include direction, if you go positive and negatives, yeah, you could have an average velocity of 0. Josh, that does not mean that you should always go against the system just because you were right this one time.
And
Say.
I
You worked out this time, you're right. Another good example would be if you went out and you ran around the track, right? Many of you have probably done the mile run outside, right? So your average speed is certainly more than 0, right? But you end up at exactly where you started, so your average velocity would be 0. So, can an object have varying velocity if its speed is constant? And the answer there is yes. Again, it's all about this direction thing, right? Give you an example. The good old St. Rose corner that I use over and over again, right? Moving at a constant speed, you're on cruise. Your velocity would be varying, but your speed would be constant. Can an object have varying speed if its velocity is constant? And the answer there is no. If the velocity is constant, that means that the speed is constant and the direction. When an object moves with constant velocity, does its average velocity during any time interval differ from its instantaneous velocity at any instant? Okay, I got to read that again. When an object moves with a constant velocity, speed and direction the same, does its average velocity during any time interval differ from its instantaneous velocity at any instant? The answer is no. Constant velocity means what? Constant speed, constant direction. Right. It's exactly the same throughout the whole thing. So the instantaneous velocity would be the same. Can the velocity of an object be 0 at the same instant its acceleration is not 0? Ooh, this is a good one. Can the velocity of an object be 0 at the same instant its acceleration is not 0? Anyone?
yes.
Josh is saying yes. Although he's not saying it in opposition to anyone else. So explain, Josh.
Uh-oh.
Okay, you just happen to be right again.
Yeah. What?
Can you explain? Just cause. Yeah. If I throw the eraser up in the air, at its peak, what is the velocity margin? 0. What is the acceleration? -9.8. Right? Because gravity doesn't know that the eraser has just suddenly reached the peak. It remains the same throughout. So there you go. There's your example. Can it be 0 at the same instant acceleration is not 0? Yes. An object at its peak. If a car has a greater maximum speed than another, does it mean that it also has a greater acceleration? A car has a greater maximum speed. I don't know, does it mean that it also has a great acceleration?
No.
No, does not. Right? Things that can go really, really fast, like rockets, space shuttles, you know, stuff like that. I guess it's not a car, but has a much greater maximum speed. The fighter jet, right, was much faster than the motorbike, but it did not have a greater acceleration. Compare the acceleration of a motorcycle that accelerates from 80 to 90 with the acceleration of a bicycle that accelerates from to 10 in the same time. Well, they would be the same, although I think that would be a pretty crappy motorbike if it has the same acceleration as a bicycle. They would be the same. Can you conclude that a car is not accelerating if its speedometer indicates a steady 60? No, same thing again. The direction matters. Should I keep going here?
Sure, why not?
Yeah? We're making good time here. Let's keep going here. Number 11, can an object have a northward velocity and a southward acceleration? Can you be going north and accelerating south? Yeah, you're just slowing down, that's all. You're going north and you're just slowing down. Can the velocity of an object be negative when the acceleration is positive? And the answer is yes. Again, you're just slowing down. What about vice versa? Yep. If the directions are opposite, the velocity and acceleration just means that you are slowing down. Give an example where both the velocity and acceleration are negative. Well, that just means that you're going right over here. This means you're going to the left and speeding up, right? Going to the left and speeding up, or going south and speeding up, I guess. If the velocity and acceleration have the same signs, then you are speeding up. A rock is thrown vertically upward with a speed v from the edge of a cliff. I feel like I need to draw a picture. A second rock is thrown vertically downward with the same initial speed. Same initial speed. Which rock has the greater speed when it reaches the bottom of the cliff? And ignore air resistance. So in other words, the initial velocity here is 5, and the red one, the initial velocity is minus 5. Which one hits the ground not later, but which one hits the ground at a greater speed? What did you guys say back there, Martin? Which one hits the ground at a faster speed? The one you throw up, the black one here? Fair enough. Josh, you want to go against him?
No.
No? You're not gonna take your chance for the third time?
No, because this is right.
He's right?
Yeah. In the air longer.
Anyone want to disagree? Come on. Austin does?
Yeah.
Are you sure, Austin? Because you'd be right! In fact, they would land at the same speed. Michaela, I can see you nodding. You were thinking that, right? They would land at the same speed because this one's going up, plus 5. Guess how fast it's going right there? Minus 5. Now, the red one's going to land a whole lot earlier, right? But they're going to land at the same speed. Right? Why? Because the acceleration is the same.
Already at minus 5 feet, just let go.
No. He didn't let go. It's thrown vertically downward. It has an initial velocity. It's projected down at minus 5. If it was just dropped, then yes, the black one would hit much faster. But they're both thrown down at the same time. Okay, I'm going to leave these ones here for another day. Okay, so we should, on Friday, we had the good fortune to go through that formula derivation, and if you have trouble sleeping on the weekend, you may have looked over that, I don't know. But let's spend a little bit of time using some of them. I got 4 examples here for you, then I'm going to give you some time to work. So a car moving along a level road increases its speed uniformly from 16 to 32 in 10 seconds. What is the car's acceleration? What is its average speed? How far did it move while accelerating? So we would have, this would be the initial velocity, the 16. This would be the final, it going from 16 to 32 in 10 seconds. That would be your time. What is the car's acceleration? So we're solving for A. What new formula has VF, VI, A, and T in it? Yeah. And I said that in a certain way on purpose. There's our new friend. I think it's the first one, right? Equation number 1. VF equals VI plus AT. Plug in and solve. You guys can do this. 32 is equal to 16 plus A times 10. Now here's all that problem solving, equation, algebra stuff that we spent so much time on in math. What do you have to get rid of first? We're solving for A, Connor. So which of those numbers are we getting rid of? You're getting rid of the 16, right? You do the opposite order of operations. So you do that by subtracting both 16 from both sides, and I really hope I don't need to continue to show that. Right? I'm going to write that as 10A because we usually put the number up front. 32 minus 16, of course, is just 16. And how do I solve times? How do I get rid of times by 10? Divide A equals 1.6. Pretty straightforward. I'm hoping that there's no math issues there with any of that. Now it does ask what is its average speed, and this is sort of one of the old ones, VI plus VF all divided by 2, and there's a reason why I'm doing this. 16, 32 divided by 2, 48 over 2, 24 meters per second. And now, how far did it move while accelerating? You guys have a fair bit of space. Put this next bit over here on the right. So you could solve this two ways. You could go V bar equals D over T. 24 is equal to D over 10. Multiply both sides by 10. I hope you know how to do this. 240 meters. I would call this kind of the grade 11 way of doing it. Can we find how far it moved while accelerating without having to find the average velocity? And the answer is yes, Mr. Bennett, with our new equation number 2. D equals VIT plus a half AT squared. And so, VI is our 16, T is 10, plus 1/2 our acceleration of 1.6, and our time squared is 10 squared. And 16 times 10, of course, is 160. 10 squared is 100. Times 1.6 would be 160. And 1/2 of that would be 80. And what do you know? The same. So I just point that out, that by going through that formula derivation there on Friday, you can avoid questions where you have to do this two-step thing. You can do it all in one. Okay, now I like to point out at this point here that this is kind of like, if you want to look at this part here in blue, the 160 times 10, if that's VI times T, that's just D equals VT. If the speed stayed at 16, it would go 160. But it's not staying at 16, it's accelerating. So this bit in red, the 80, is how far it goes because of acceleration. Okay? So it's really sort of a combination of these two. 240 meters. That's pretty easy. That's the one you guys have, a ball initially rolls down a hill. I see I've got pictures on mine. I'll make that bigger. That's pretty small. Want to try this one on your own? How much space you got? Or you want me to do this one? I'll do this one. I'll let you get going on number 3. A ball initially at rest rolls down a hill with an acceleration of 3.3. If it accelerates for 7.5 seconds, how far will it move? How far would it have moved if it started at 4 rather than from rest? So we've got initial velocity 0. We've got the acceleration, and we've got the time again. How far will it move? It sounds a lot like this one I was just doing. G equals VIT plus a half AT squared. I say it out loud so that you remember it over and over again. At rest. Oh, so what happens when it's at rest? VIT. 0 times 7.5, but that whole thing is just 0. Plus, that's a 7.5. A very poor 7.5. Plus 1/2 acceleration, 3.3, 7.5 squared. And figure it out. $92.8, Josh? Do you need to show this whole 0 thing over here? No. Oh yeah, that's pretty straightforward. How far would it have moved if it had started at 4 meters per second but had already been launched? You do exactly the same thing except you put a 4 in there. Four times 7.5. $122.8. These aren't hard, are they? I hope you're not finding it hard. If you are, we'll have to do some work. In this one here, we've got an acceleration of 1.4, started from rest. What distance would he reach a speed of 7? Oh! This one doesn't have time. So, no problem. We just go to the third one, which is VF squared equals VI squared plus 2AD. So, 7 squared, initial velocity 0 squared, 2 times 1.4. Solving for D. Well, I guess the algebra here is a little bit tricky. 7 squared is 49, 0 squared is 0, 2 times 1.4 is 2.8. Okay, hang on, I lied, it's not that hard. All right, divide both sides by 2.8. 49 divided by 2.8. Well, who's got an answer for me? 17.5 meters? A longer way, Tanner?
Sure.
Yeah? Solve for time first? Possible, yeah. Don't forget about this one. Okay. You want to try number 4 now? Who needs a little time to try 4? Nobody? Did you want to try number? I'd like you to try number 4. Okay, you guys try 4. Here we have a plane starting from rest at one end of a runway, undergoing a constant acceleration of 1.6 for a distance of 1,600 meters, which is about a mile, exactly a mile. For takeoff, what is its speed upon takeoff? So we have VI, we have an acceleration, we have a distance, and we want to know the speed upon takeoff. So I think that would be VF squared equals VI squared plus 2AD. We're solving for VF. The VI is 0, that's always nice. 2 times 1.6 times 1,600. You should be able to do that all in your calculator in sort of one step. 2 times 1.6 times 1600, and then don't forget to take the square root. 71.5, is that what you got? Yeah? 71.5 meters per second, which just happens to be 258, I guess, kilometers per hour. Does that seem reasonable? Planes go pretty fast. Not that fast, Martin? I don't know, they go pretty fast. What is the time required for takeoff? Now, there's a variety of ways you could do that, but I think the simplest would be VF equals VI plus AT, so 71.5, initial velocity 0, acceleration of 1.6. We're solving for time. So really, it's just 71.5 divided by, 1.6. Forty-four point 7 seconds. Does that seem like a long period? Who's been on like a big plane, right? Most people have. A lot of people have. Is it 44 seconds, you think? 45 seconds, Bailey? Yeah, you think so? From like start to finish? That's a long time. Yeah? Okay, well, the next time you're on a plane, you time it. Oh, no, I mean like from actually starting, Tanner, not like, the entire...
Starting as in...
Like when they actually turn the engine, start moving, yes.
Or not when they're like...
No, not when they're taxiing, no.
Oh.
Or waiting there at the end of the runway for them to de-ice, or for them to get rid of a small plane that's lost a wheel or something around the runway.
Wet.
Actually, I think it's probably more like 20 seconds.
No,
Which of those numbers do you think, Sean, is not likely? Well, we're getting 44.7, but which one of the given numbers? Yeah. Like the mile long? You think a runway is a mile long?
One big plane I went on, it was like a double decker.
Oh yeah? Yeah. I would think a mile would be reasonable. What about the 1.6? That's pretty low, eh? Yeah, we generally don't have a good understanding of what kind of acceleration. My guess is that acceleration is pretty low. Should probably be 3 or 4 times that. But anyways, next time you're on a plane, just time it and see. Okay, I'll be quiet. You guys got some problems you can work on there. I'll give you the rest of this period. Tomorrow, bring textbooks. I'm going to be doing some challenge questions out of the textbook. Wednesday, we'll look at the Fred and Barney style questions, which are challenging. And then you'll likely get the first pretest either Wednesday or Thursday. Okay? We'll spend a little time doing some problems. That is all.